Introduction. Birth of stars is one of the most fascinating and fundamental processes in the universe. These celestial giants illuminate galaxies, forge the elements necessary for life, and shape the very structure of the cosmos. Yet, their origins are anything but simple. For centuries, scientists and thinkers have pondered the mystery of how stars come into existence. From early philosophical musings to the cutting-edge physics of today, our understanding of star formation has undergone a radical transformation. In this video, we'll journey through the evolution of scientific thought, uncovering the ideas, theories, and evidence behind how stars are born. The earliest questions, before science and long before telescopes or particle accelerators, ancient cultures stared up at the night sky and created stories to explain the twinkling lights above. The Babylonians, Greeks, Chinese, and many other civilizations wove myths around the stars, often tying them to gods or supernatural beings. These early interpretations, while unscientific, reflected a deep curiosity and awe toward the stars. However, the concept of stars being born was alien to these cultures. Stars were seen as eternal, fixed lights embedded in the celestial sphere. It wasn't until the scientific revolution that humanity began to ask, what are stars? Where do they come from? And could they have life cycles, like living beings? The shift to scientific inquiry in the 17th century, thinkers like Galileo and Kepler began using mathematics and observation to describe the heavens. But it wasn't until Isaac Newton introduced the law of universal gravitation that a foundational piece of the puzzle was placed. If gravity pulls matter together, could it also cause large clouds of gas to collapse and form stars? This question would linger for centuries. Observers saw nebulous regions in the sky, glowing clouds like the Orion Nebula, and speculated about their nature. Were they remnants of dead stars, or perhaps the cradles of new ones? The Nebular Hypothesis. In the 18th century, French mathematician Pierre-Simon Laplace proposed the Nebular Hypothesis, suggesting that stars and planets formed from rotating clouds of gas and dust. While his model focused primarily on the formation of the solar system, it planted a crucial idea: celestial bodies could form rather than simply exist. Later refinements of this hypothesis imagined stars forming within vast interstellar clouds, the birthplaces of suns. This laid the groundwork for the modern concept of star formation. Understanding interstellar clouds. The next step came with the discovery of interstellar medium ISM, the diffuse gas and dust that fills the space between stars. In the 20th century, astronomers began mapping these regions in radio and infrared wavelengths, revealing vast molecular clouds where temperatures were just a few degrees above absolute zero. These molecular clouds, often called stellar nurseries, contain the raw material for star formation, primarily hydrogen molecules. Within these clouds, gravity can cause denser regions to collapse, initiating the star formation process. Young's instability and the physics of collapsing. In the 1920s, British physicist Sir James Jeans introduced a mathematical framework to explain when and how a cloud of gas might collapse under its own gravity. Known as Jeans' instability, the theory posits that if a portion of a cloud is large and cold enough, gravitational forces will overcome internal pressure, triggering a collapse. This collapse doesn't happen evenly. Instead, pockets of gas fragment and collapse at different rates, leading to the formation of multiple stars, often in clusters. As the gas collapses, gravitational potential energy converts to heat, raising the temperature at the core. Protostars. A star is born as the collapsing cloud heats up. A protostar forms at the center. This young object is not yet a star, as nuclear fusion has not begun. Surrounding the protostar is an accretion disk, a swirling mass of material, feeding the growing object. Over time, the temperature and pressure in the core rise. Once the core reaches about 10 million Kelvin, nuclear fusion ignites, primarily fusing hydrogen into helium. This marks the birth of a true star. The energy released from fusion counteracts gravity, stabilizing the star into what we know as the main sequence phase. The role of angular momentum and magnetic field star formation is not simply a matter of collapse. Angular momentum plays a critical role. As the gas collapses, it spins faster, much like a figure skater pulling in their arms. This spinning motion flattens the cloud into a disk, which can eventually lead to the formation of planets. Magnetic fields also shape the process. They can slow the collapse, channel material into jets, and regulate how mass flows onto the growing star. Observations of bipolar outflows, narrow streams of gas ejected from protostars, reveal how magnetic and rotational forces work together. Observing star formation today thanks to modern telescopes like the James Webb Space Telescope JWST and ALMA in Chile, astronomers can now peer deep into stellar nurseries. Infrared and radio wavelengths cut through dust, allowing us to observe protostars and young stellar objects in exquisite detail. These observations confirm much of what theory predicts: disks, jets, accretion, and fragmentation. They also raise new questions. Why do some clouds form hundreds of stars while others form only a few? What triggers the collapse in the first place? Supernova shockwaves, galactic collisions, or turbulence? High-mass stars versus low-mass stars. Not all stars are born equal. High-mass stars, those larger than 8 solar masses, form more quickly and burn hotter. Their formation is more violent, with stronger radiation and winds that can disrupt surrounding clouds. Low-mass stars, like our Sun, take longer to form and can live for billions of years. The environment also matters. In dense stellar nurseries, interactions between forming stars can influence mass accretion and disk stability. In isolated regions, stars form more slowly and quietly. The role of chemistry and dust. While hydrogen dominates, trace elements and dust grains play a pivotal role. Dust helps cool collapsing gas by radiating heat away. It also forms the basis for complex molecules, including organic compounds that may eventually see planets. In some regions, the presence of heavy elements created by previous generations of stars enhances cooling and leads to more efficient star formation. Thus, the chemical evolution of galaxies directly influences how and where new stars can form. Population 3 stars. The first lights. A major question in astronomy is, what were the first stars like? These so-called population 3 stars formed from primordial gas, mainly hydrogen and helium, just a few 100 million years after the Big Bang. Without heavier elements, they behaved differently from modern stars. Simulations suggest they were massive, short-lived, and critical in shaping early galaxies. Though we've never directly observed a population 3 star, astronomers hope next-generation telescopes will detect their faint signatures, unlocking secrets of the early universe. The cycle of star formation. Star birth is not a one-time event. It's part of a grand cosmic cycle. Stars form from gas clouds, shine for millions or billions of years, and eventually die, sometimes in spectacular supernovae. These deaths scatter elements like carbon, oxygen, and iron into space, enriching future generations of stars. This cycle of birth, life, death, and rebirth drives the chemical evolution of the universe and makes life possible. The atoms in your body were once forged in stars. In a very real sense, star formation is the story of how we came to be. Modern frontiers and theoretical challenge. Despite enormous progress, many mysteries remain. What precisely triggers star formation? Why do some clouds remain dormant while others burst into activity? How do magnetic fields, turbulence, and cosmic Rays influenced the process. Advanced simulations running on supercomputers now attempt to model entire galaxies, including individual stars. These models grow increasingly realistic, but still struggle with complexity. As observational data improves, theory must catch up. Conclusion: birth of stars is more than just an astronomical process. It's a story of gravity, heat, chemistry, and time. It's the story of matter organizing itself into brilliance, of darkness giving way to light, and it's a story still being written. Every time we look up at the night sky, we witness this ongoing miracle. Behind each star lies a history of collapse, fusion, and cosmic choreography. And in understanding how stars are born, we take one step closer to understanding our own origins.